Okay, yeah, please, Yuri.
So we'll continue my last week's talk. Let me recall where we left off. So we were considering for the most of the talk four-dimensional manifold with a generalized complex structure, which we think of using this classical bi-Hermitian setting. There is a metric G and there is two compatible complex structures I and J, and we have several extra assumptions on this. So we first assume that the structure is even, that is, these two have induce the same orientation. So if we assume this, then unless I equals plus or minus J globally, which we don't consider because it's sort of trivial for our purposes. So if I is not plus or minus J globally, then I and J is invertible at generic point. So assume for a second that it is global invertible. And we assume also that there is S1 action on M generated by the vector field X. And for now, for a second, let's assume that it is free. And yeah, when I say it's an action of M, I assume that it also preserves all the structures. So it's killing and it's real holomorphic with respect to either I and J. So with this setting, we have Gibbons-Hawking ansatz. That is a local description of such structures. So, and so far, I don't need really a Solidon equation. I don't need any assumptions about completeness. It's completely, it's general in the sense that it gives you an exhaustive local description under these assumptions. So specifically to cook up such an object up to universal cover. So this universal cover business, it has to do with the fact that the action of S1, it might be not Hamiltonian with respect to symplectic forms naturally attached to this picture. So you need to take cover to make it Hamiltonian, but if you worry only about local pictures, you don't even need to consider that. So to cook up such an object, you need several pieces of data. So you need three-dimensional manifold openly mapped to R3. You need function P defined on N. With the range -1 and 1. And you need function V, which is just positive. So this is smooth functions. So this will be angle function. So this will be trace -1/4 trace of ij. And this will be the inverse norm squared of vector field X. So, and for the construction to work, they have to satisfy the compatibility conditions. So there are several of them. So first is that there is form. Yeah, okay, maybe I should mention that function P defines explicitly a metric R3 on H. So maybe I'll write it explicitly to recall that setting. So P defines a metric H. Well, it actually lives on N. And we can write it explicitly in coordinates if we would like to. And with this metric, we also can write two form. Did I have that somewhere? In a second, let me. I just don't want to mess up with a sign. It's not really that important. Yes. So defines a metric and a two form, and the assumption is that the following two form, which you can cook up from this data, specifically star dv plus v times beta 0. So we want this to belong to the integral homology of n. And is closed. So this, you want this form to be closed, and you want to its class. Maybe I'm a bit vague here. So class of this form, you want to be an integral class. So this being closed is equivalent to elliptic equation. Elliptic equation on V with the leading term Laplace HV. So it's very similar to the classical Gibbons-Hooking ansatz for hyperkähler structures, but there are extra features and maybe extra difficulties. Then on the principal bundle, S1 bundle with curvature beta. So let me recall, denote this bundle by M0. So it's a bundle over N0. This is something 4-dimensional. This is something 3-dimensional. There is a GK structure.
Yuri?
Yes.
Can you please hide the pencils on the right-hand side of the screen? Because I don't see the, yeah, thanks.
Yeah, sure. Sorry about that. So there exists a generalized Kähler structure with the metric. I mean, with explicit metric and explicit complex structure. So maybe I'll write the metric. So with metric G given by VH plus V inverse eta squared, where the eta is connection 1 form. For this principal bundle. So this is how the metric look like, and the holomorphic symplectic forms which define complex structure, they're also fairly explicit. Maybe let me write it. So omega I will be a holomorphic symplectic form. So this defines the complex structures, structure I, by the condition that this will be an element in lambda 2 0 with respect to I. So this uniquely prescribed I. And omega J is sort of obtained in a symmetric way by swapping 2 and 3 and changing some signs. So this belongs to lambda 20J. So this procedure, this input data defines necessarily generalized scalar structure, and vice versa. Any generalized scalar structure with assumed restrictions that Ing are the same orientation, and the commutator of Ing is global invertible, and the action is free, so it arises necessarily through this ansatz. And if you're really working on a ball in R3, for instance, if your three-dimensional manifold is just a subset of R3 and an open ball, then, for example, this condition became vacuous. You don't have any second homology. And really, the only condition which you have is this elliptic equation. And just a remark what this elliptic equation, this construction shows is you can choose P essentially arbitrarily. It can be any smooth function. And for any choice of P, at least locally, you will be able to solve this equation V. So any germ of the angle function P can be obtained for the appropriate choice of V. It shows that at least locally, the generalized scalar structures, they are really abundant. So you can take any smooth function P, and for it, you can take locally any solution to the elliptic equation, and there are, of course, plenty of those. And you will still get a generalized scalar structure. So without extra assumptions, there is no real hope for any sort of rigidity. So we need to throw in extra assumptions about our generalized scalar structures to get some reasonable problem which could be solved.
If you just vary P,
Yeah.
is there a way to kind of so when you vary P, I guess it changes this Laplacian or this L elliptic. So can you kind of solve it in families? So you
this equation will be changing. I don't see, I mean, maybe, I mean, because there is many structure here. Maybe there is a way, but I don't see it off the top of my head. So not for some obvious reasons.
and is V essentially unique up to?
If it's a local problem, no, it's not unique. You can solve the Dirichlet problem essentially. You can prescribe V on the boundary and extend it in a unique way in the interior of your region. So for any boundary value, you will have some V inside. Well, I should be a bit careful here because you also need like the boundary value to be positive, so the solution stays positive. But yeah. There is no like even resemblance of uniqueness here. It's very generic. There are more questions. So what we're going to do today, we're going to find a specific setting for this ansatz, discuss specific setting for which the problem becomes rigid and becomes sort of classifiable and a reasonable problem. And this goes back exactly to the Soliton equations, which we discussed for the last 2 weeks. What we're going to do further is to throw in rank 1 Soliton equation. So let me recall what it means. It means that there exists a function f such that the vector fields vi and vj satisfy IVI is proportional to x and JVJ is proportional to x. maybe constants of proportionality that let's call them AI and AJ. So, or if you want to discuss from the other end, we'll know a priori that IVI and GVJ are both killing. And rank one assumption is essentially the assumption that they are aligned with each other so that the isometry group is as small as possible.
Or maybe biggest.
It can be bigger in principle, yeah. Or did you want to?
On a homogeneous space, maybe they will be on.
So yeah, this is our first assumption, and the fact that that X is a vector field preserving Gi and J, it's a large part of Solton equations, but not all of it. So you have this extra equation that should I put it? There are several ways to write it down. I've already disclosed it. LVI of omega I equals Bismuth-Ricci 1,1. So these together give you the complete description of the Solton equations. Alternative to this classical one, maybe I'll write down once again. So the fact that these are so the fact that VI and VJ are individually I and J holomorphic, and IVI and GVJ is killing, which is of course true under these assumptions. Together with this equation, these imply the system which we were writing in the beginning, in the classical terms, without using of complex structures really on the generalized geometry. It will look as follows. So H star H plus fashion F equals 0, and T star H plus so this was the equation which we wanted really to solve. All right, so let's see how the setup is different from what we discussed before. So now I and J is generically invertible. But fails to be on this special degeneracy locus, which will denote T. This is where I equals plus or minus J. So this locus is present, and we know it from the examples. For example, from the Hopf solitons, these two loci are precisely the support of the canonical divisor on the Hopf surface. So we have to allow for that. And another difficulty that X, the action of the circle on manifold, so generated by X, is not free. And there are several phenomena here which occur. So it happens to be not free in several ways. So of course, as in Haber-Keller case, so it's not really something new. They might be isolated fixed points. So this is not really big of a deal. But the bigger problem is that S1, it preserves, of course, this the degeneracy locus because it preserves ing. So the action restricted to this divisor might have finite isotropy groups. And the main issue is that, in particular, if you want to consider the quotient space, and this is really the main object which we'll be trying to recover, a priori it's just an orbifold. So we have to deal with that, and we have to deal with orbifolds necessarily. And the examples which we'll construct, we'll see orbifolds. Okay. So the first step, the first thing which we will do to make our problem rigid, which we will show that this equation, again, kind of complicated nonlinear equation, in this specific ansatz above, this given square ansatz, reduces to a very simple equation, and essentially it prescribes you function p. This is kind of one of the biggest sources of flexibility in this ansatz, that function p can be arbitrary. So now we will show that Sultan equation is equivalent to prescribing function p in a certain finite dimensional family. So let me explain this part first. Proposition. So, under the ansatz above, under this given squaring ansatz, generalized Keller-Sultan equations. Well, actually, this is true in general. What I'm about right now. So, in general, generalized Keller-Ricci-Sultan equations imply that locally there exists potentials psi vi and psi vj. So these are just smooth functions, and they will be supported on m minus t. So they live on the non-degenerate locus of generalized complex structure. So where I is not plus or minus j. So if I is not a plus or minus j, we can define a symplectic form omega. And I'll just write it on the top. So omega is I j inverse g. So it's a symplectic form. So Sultan equations imply that this vector field vi and vj, they necessarily preserve omega. So it's true on any generalized Keller-Ricci soliton. So this must be an exact form. So locally we can write it as psi vi, and similarly I vj omega will be d psi vj. Because the flow of the Sultan vector field preserve in either I fixed gauge or j fixed gauge preserves this symplectic form. Then the claim is
sorry, Yuri, the conditions on the action are assumptions, or you can prove that from the generalized scalar soliton.
Yeah, this you can, the existence of local.
No, the conditions on the action, on the S1 action.
Yeah, these you don't need Sultan equations for this too.
Sorry, I didn't answer.
You do not need Sultan equations. It's true in general. It's true in general as long as you have this given squaring ansatz.
Okay. Thanks.
So given squaring ansatz essentially tells you that you have S1 action which preserves G, I, and J. Okay, so okay, maybe I'll just leave this revision as is. So it's kind of a general fact about solitons. And the next position will be specific in the given squaring ansatz. So in Gibbons-Hawking ansatz, we know what VI and VJ are. So VI will be essentially mu2 and VJ is mu3. That's how we constructed this moment maps. And the actual claim here that special function which is equivalent to function p. So function p can be converted, instead of considering function p, we'll consider function p, which is defined to be log 1 minus p over 1 plus p. So this function then is necessarily, so we have ai and aj, because where ai and aj are these constants. So then the claim of this proposition is that this function phi, defined as log 1 minus p over over 1 plus p, is 2ai mu2 minus 2a j mu3 plus a constant. Generalized Taylor-Sullivan equation implies that phi is fixed, and phi being fixed implies that the function p is fixed. And really the parameters which are essential here are ai and aj. So this constant which appears here, it's inessential because it could be absorbed by redefining the moment coordinates. So moment coordinates defined up to adding a constant anyway.
I'm confused. What are U2 and U3? Because you had them initially as vector fields, and then they're
No, mu2 are, sorry, did I have them as vector fields? These
Well,
ones.
you said VI is equal to AI U2,
Vi is equals to AIX.
but then below.
And mu2 are defined, yeah, maybe I should have, let me remind it from the last lecture.
Just there, when you write in GH ansatz, VI is equal to AI mu2 in the proposition.
Oh, that's a type. That's meant to be psi Vi. Thank you. Thank you. Yeah, because the way we define mu2 and mu3 is that I might be a bit sloppy about sides. I think it's like this: Ix omega equals t mu2.
So the global definition of mu1 and mu2 is a part of the ansatz?
Well, so far, this is a local picture, right? So I mean, to write down this proposition, since Generalized Taylor-Sullivan equation is local, so this is also a local statement. So I assume that I'm working on a patch of a manifold where mu2 and mu3 are honest functions. Does answer your question?
Mu2.
Yes, but you want to construct examples in which mu1 and mu2 and mu3 will be globally defined. Is that correct?
In some of them they will, and some they will not. I will have both. There will be both
Okay,
of those examples. Yeah, Francis, you have a question?
No, I'm good. Thanks.
Okay, thank you. So the proof is really just the use of this identity, which Vesti and Jeff found in their paper. So this identity tells that on any non-degenerate generalized scalar manifold, so you still can define this function phi. So this definition makes sense in dimension 4. You can change the right hand side so it will make sense in any dimensions. Basically, you just put it to be log determinant I plus j over determinant I minus j. So on any non-degenerate scalar manifold, there is an identity that if you hook in the difference of Lie vector fields into omega, then you'll get d phi. And on a soliton, theta I sharp minus theta j sharp is exactly twice vi minus twice vj. And we also assumed, being rank 1, that vi is ai x and vj is, sorry, yeah, might be off with signs. So really, that's what we assumed. So in particular, vi is negative ai ix, vj is negative aj jx. So in particular, therefore, what you have here is negative ai d mu 2 plus twice aj d mu 3 equals d phi. And that proves that phi differs by a constant from this. Again, signs are off. Maybe to correct, I put here like this. Okay. So bottom line here is that Sultan equation uniquely prescribes angle function under this assumption of rank 1 Sultan.
Sorry, I'm not sure if I understand. So at the beginning of the proof, you said that in a non-degenerate generalized scalar manifold,
Yes.
you have that this contraction with big omega is d phi. So what is the definition of phi at this point?
Either this one or this one in 4 dimensions, they're equivalent.
Yeah, but the p is part of the, I mean, you are trying to prove something without assuming the, yeah, I'm not sure.
So you first, so if you have any non-degenerate generalized scalar manifold, you can consider this function phi. Right, say we're in dimension 4. Then you will have this identity. Now let's assume you have a soliton. So if you have a soliton, then the difference on this Lie vector fields is the same as a difference of the soliton vector fields vi and vj, just by the definition of vi and vj. And on rank 1 soliton, that's our standing assumption. The IVI is proportional to x and GVJ is proportional to x. So this difference is really the difference of vector fields AI times IX and AJ times JX. So what we're computing on the left-hand side is symplectic potential for the difference of these two vector fields. But we already know the symplectic potential through the moment function. So the symplectic potential for the difference of these two vector fields is 2ai mu2 plus net minus 2aj mu3.
But so if I understand, the p in the formula for phi is defined as -1/4 trace I composed with j. Is that true?
Yes.
Okay. Okay. And this is a priori defined in terms of just the general scalar structure. Okay.
Yes, it's intrinsic to general scalar structure. Yes.
Okay, thanks.
So conversely, so here we assume that we start with generalized scalar soliton, and we saw that we can prescribe phi. So conversely, if phi is a sublinear combination of mu2 and mu3. Again, maybe I'll write the same combinations. 2ai mu2 plus 2aj mu3 plus constant. Then first the form we can write let me be a bit slower. So let p be the function of u2 u3 such that phi equals log 1 minus p over 1 plus p. So we just invert this expression. Let m g I j be a GK generalized scalar structure corresponding to Gibbon's Hawking ansatz. With the given p and any compatible function v, any compatible. By compatible, I mean that it solves that set elliptic equation and assumed homology class is integral. So this is the two assumptions in function v. Then the one form p times d 1 over 2 p times sorry, let me do one thing. So before I describe this converse part, I want just to introduce a notation which will be a bit more convenient for what I'm going to write. Notation. So it turns out that most of the formulas, and like geometrically, it happens that mu2 and mu3 are not the most convenient coordinates to work with on this image, on the domain of the image of the moment map. So we introduce mu plus to be mu2 plus mu3, and u minus to be mu2 minus mu3. From the point of view of generalized scalar geometry, these moment functions for two symplectic forms, for f plus minus. And then I will write that phi equals a plus mu plus a minus mu minus plus constant, where plus and a minus are just expressed through ai and aj through this linear change of variables. It's not really important. It's just easier to write down most of the formulas which will appear. So if you have, conversely, if you start with phi with just linear function mu plus and mu minus, and you choose the corresponding angle function p, and you choose compatible v to cook up generalized scalar structure through Gibbon's Hawking ansatz, then it I would like almost to say that it will be a soliton. It will be almost true with one little caveat, and I just want to say what this caveat is. So first thing which I wanted to say that the form
Can you recall how did A plus and A minus, how did you choose those?
Yeah, give me a second. So let me finish writing this. Right. So I have phi given being a linear combination of mu2 and mu3 with coefficients negative to AI and to AJ. Now I make a linear change of combination, linear change of variables. Instead of mu2 and mu3, I consider as my variables mu plus and mu minus. And just I express mu2 and mu3 through mu plus and mu minus. And substitute here, and then I will have some, again, constant terms in front of mu plus and mu minus, which are expressed through AI and AJ. So these are just two real numbers. And they carry the same information as AI and AJ. Does that answer your question?
I was asking if when you start with, like when you're building the Gibbon-Hawkins ansatz, I guess you're starting with R3 and mu plus and mu minus are two coordinates or something.
Yes.
And then are you free to choose A? To
Yes.
be any...
Yeah. All right. Okay. Yes. Sorry. At this point, you're allowed to choose A plus and minus to be just any two constants. Any two real
and then
numbers.
you get that's like your input for the construction.
Yes. Yes. Later on, when we will be resolving completeness questions, we will see that actually A plus and A minus, they are quantized. They can take on only discrete set of values. But for now, for this part, this could be any real numbers. So conversely, so you start with such phi, you cook up corresponding angle functions and take some compatible function v, and you realize it through Gibbon-Hawkins ansatz, some generalized scalar manifold. So on this generalized scalar manifold, you will have this one form. So this one form is closed. And if it is exact, then denoted by df. So where f is just smooth function of the manifold. And then the claim is under exactness assumption. Gij is a rank 1 soliton with Vi being theta 1/2 theta I sharp minus grad f being the same as so again, AI can be computed backwards from A plus and A minus from these two constants. I don't want to mess up with all this constants and signs. So I'll just write this as and Vj 1/2 theta j sharp minus grad f, which will be the same as AJ. Sorry, yeah, I meant to put negative Jx. Okay. So it's almost like a soliton, but for the soliton, we have this, from this point of view of equations, somewhat arbitrary requirement that the corresponding vector field is truly gradient and not just locally gradient. So if you want to impose that, you have this exactness assumption. So anyway, bottom line is that you can choose any two real constants, A plus and A minus. You can consider the corresponding angle function. Again, locally, you have abundance of solution, abundance of compatible functions V solving the necessary elliptic equation. And for any choice of V, again, at least locally, because locally you will not have exactness issue, you will have rank 1 soliton. So the picture goes as follows. So you start with R3. With this mu coordinates, you maybe take some patch on which you consider the prescribed function P, and you solve the elliptic equation. So you find also function V. Then over this patch, you will have a principal S1 bundle. And on this S1 bundle will be rank 1 soliton. So again, what it shows a kind of, again, phenomena which is known for other geometric PDEs, that when you don't consider compact or complete solutions, but only local solutions, usually you will have many of those. And the difficult question, the hard question, when they can be compactified or completed into something smooth and nice. And, most often, if you just take some kind of generic solution of this equation, you will not be able to complete it into complete soliton. Okay. Other questions to this point? So let me now discuss what we need to understand to classify complete rank 1 solitons. So if you have a rank 1 soliton M, let's first consider M0, which will be M minus fixed points of your action S, of your circle action. Fixed points. And then let's consider actually M0 minus T then. So we throw away this locus where I equals plus or minus J. We have S1 acting on M0 minus T. So I claim that we can can take a cover. So it's not universal cover, it's some partial cover. Such that S1 lifts to a tri-Hamiltonian S1 action on this cover. So, and as such, M0 minus this T cover is given by Gibbons-Hawking ansatz. With phi so over some unknown, some a priori unknown, and which is openly mapped to R3. Okay. So we want to travel this path sort of backwards. So we want to understand, so for which solutions over some n mapped to R3, we can really first construct this gadget through Gibbons-Hawking ansatz, then quotiented by some deck transformation group, to get back M0 minus T. And then complete it by gluing back first this divisor and then fixed points. And at the end of the day, obtain something smooth and complete. So we want to travel this this path, this construction backwards to do the classification.
So could you tell us what is the reason of this claim that you can always find such a cover?
Yeah, I mean, so how this cover works. So okay, let me spend some time discussing the structure of the cover. So we can consider three forms. We can consider alpha 1 to be ix omega. We can consider alpha 2 to be ix omega. We can consider alpha 3 to be jx omega, right? And they might not be they're close, but they might not be exact. So let's resolve this non-exactness. How exactly it works. So they are not exact essentially because they integrate by something non-zero over some cohomology classes. So let's denote it maybe the set of cohomology classes, homology classes over which alpha I integrate into 0 by k. And then what abstracts the vector field to be trihamiltonian is quotient H1 mod gamma. So H1 is first homology group. Yeah. So this sorry, mod k. So this abstracts X to be tri-Hamiltonian. But then you can see, yes, and what the cover is then. So the cover exactly is the cover corresponding to the Dirac transformation group gamma. So you have a map from fundamental group to gamma, this the projection, and this Dirac transformation group, which which appears in this cover, is exactly group gamma. So what could happen? You're right that S1 action lifts only to R action here. But if that happens, it means that the representative in the fundamental group of the orbit of S1 action leaves, survives to gamma. So it gives you non-trivial representative in gamma. All right, so you have this S1 action on M, so you can take one orbit, and this orbit will become disconnected when you take this cover exactly when the class of this loop, well, it's only defined up to conjugacy, but it doesn't matter since you quotient to the abelian part. So if this guy is a non-trivial element in gamma, but you can immediately observe that the representative of any orbit actually lives in K. Because if you hook in X into alpha 1, alpha 2, or alpha 3, you'll get 0. So if this is orbit of S1, so gamma is S1 acting on some point X, then integral over gamma of any of alpha I is 0.
Yeah, I'm satisfied from your explanation.
Okay.
You can
So yeah, the real reason that all these forms integrate to 0 over the orbits of S1 action, so S1 action doesn't disconnect. So let's discuss kind of big parts of what we need to do to travel this path backwards to actually recover from this Gibbons-Hocking ansatz, which has many unknowns, which we have to determine how and when we should be possibly recover M. So let's list what we need to understand. So first thing which we would need to understand is the structure of omega and x near the degeneracy locus. Because this is something what we do not see really in Gibbons-Hocking ansatz. We kind of we throw it away. So we need to understand at least some coarse local structure of those. So second part, we really want to understand image of the moment map. So the moment map, or the moment map, yes, from M0 tau to R3. And also its relation to the quotient space. So you have S1 action on this free S1 action. So how it is related to this quotient space. So this is what we call N0. So what will happen at the end of the day that this N0, this quotient space, must be entire R3. So this open map, unknown open map, really becomes just makes N an open subset of R3, and this open up subset is just a complement of a discrete set of points, of isolated points in R3. And this is where we will heavily use both the Solton equation and the completeness property. So third part, we want to understand the structure of the deck transformation group. Deck transformation group in this covering. So you have this covering, you have gamma on 0 minus t. So deck transformation acts here. So we want to understand how it acts here and what would be the action, the action which descends to the quotient. So this action will commute with the action of S1. So it will descend to the quotient, what exactly this action is. And so next part, we will really we'll need to study possible completions of what you can cook up from the Gibbons-Hocking ansatz modular your deck transformation group. So you really want this to be you should be able to complete it into a smooth manifold, and that will be the restrictive assumption. So far, we didn't really talk about this function V, the extra ingredient, which was at the moment, which is the source of all the flexibility and the reason why we haven't defined rigid families of examples. And that will be sort of the final step. Classify solutions to LV equals 0, which give rise to complete rank 1 solitons. So I sort of write it in vague terms. I will maybe specify it if I have time. So I will probably talk more about part 2 and then talk a bit about part 1. I will maybe actually we'll have to skip most of this part. So well, let's see. That's how it goes. So structure of omega and x. So maybe let me just write the statement. So for this part 1. we can cook up holomorphic 2-0 form, right? Which will be omega minus square root minus 1 I omega. So it's a holomorphic, is an I holomorphic symplectic form with a pole along I equals plus or minus G. Okay, it's not really a lemma yet. It's just a setup. So a lemma tells us that this omega I has a pole of order 1. Along any irreducible component of this divisor. So this divisor could have several components, and they could have several components intersecting. So along any of them at that smooth point, it will have a pole of order 1. And X is not, the vector field X is not identically 0. On I equals plus or minus G. So the proof really uses the fact that on the universal cover of the open part, we have Gibbons-Hawking ansatz, and uses, this is kind of the main input, and uses the fact that we know exactly what the angle function is here. Probably I will just skip the proof of this lemma. So it's sort of not that hard to get from the local description. Not even local, it's already global description of this as a Gibbons-Hawking ansatz. But it already shows that solutons are special, right? Because through this deformation along Poisson tensors construction, we know that in principle we can cook up generalized scalar structures where omega I or respective has a pole of order more than 1, or respectively Poisson tensor has a vanishing of order more than 1. So you have higher order vanishing, but it doesn't have it on solutons, at least on rank 1 solutons. So this was about this part 1, understanding the core structure of omega and X near the generalized locus. So the really interesting part is the image of mu. This, I would say, technically one of the hardest part of the entire classification result. And to this end, I would like to discuss a more general setting. Consider a more general setting. So let's assume that we have a base manifold, maybe N, and we have a metric H, and we have 2 form beta 0. So they're not related to any angle function or anything like this. So this is just metric and then 2 form. And you have a principal bundle over it. So this will be M, principal bundle, such that curvature of this principal bundle is star dv plus beta 0v. So this is something what you have before. And you have a metric upstairs, which is v times h plus v inverse times eta squared, where eta is a connection 1 form. And we also need some tameness assumptions. So maybe let's assume that norm of beta and norm of its derivative is bounded on N. So N is not assumed to be compact, and it will be not compact, as it happens in the examples which we saw before. And we also assume that Riemannian, some sort of control of geometry on N. And we also assume some weak control over geometry on on M before we assumed on N. So the Ricci is just bounded from below. So the claim which I want to make here, actually we'll need more in the proof, but I mean, all the essential parts will be seen here. So the claim is that N if G is complete, then and H is also complete. So it looks like an innocent statement, but really it will have a lot of consequences for our purposes. So specifically, what we'll have in our case. So this thing is not really complete because we have thrown something, but we can control its non-completeness. We know how exactly it occurs, and the way this proposition below how it will work, that the image of under the moment map here will have to be R3 minus discrete collection of points, and this discrete collection of points, they will exactly correspond to the fixed points of S1 action of M. But because we threw away these fixed points, we will remove them from here. So if you glue them back, which you can do, of course, for the classification purposes, then your image will be the entire R3. So it sort of resolves the issue of what this N could be. So it will force N to be just the quotient space of this module S1 action. It will force it to be R3. So that's why it's an important result. So let me talk a bit about the proof. So proof is a bit technical, maybe kind of obvious remark that MG complete then due to the special form of the metric. So the metric looks like this, and with respect to metric VH is complete. The problem is that V could blow up potentially, and if V blows up, even though this metric space is complete, this might not be complete. So there might be a curve of finite length here escaping to infinity, which becomes a curve of infinite length here. So, and it tells you that essentially you want to get some control over V to ensure that it doesn't happen. And step one really is to use the fact that the curvature form is given by this expression. So in particular, this must be closed, of course, since it's a curvature form. So the fact that it's closed gives you second order elliptic equation on V. And it happens that it will be equivalent. So this is equation essentially on N. But you can consider the same function on the upstairs on the manifold M, and the corresponding equation on M will be something like Laplace equation with respect to metric G of your function V equals V inverse multiplied by a bunch of stuff, which you essentially can control. So exact form is not really important. Not that important here. Sorry, W is V. Basically, on your complete four manifold M, V solves an equation like this. It's almost like Laplace equation, but it has this a bit nasty term on the right. But it turns out in the end that it's not that bad. And what you can do, you can apply to this equation, Cheng-Yao gradient estimate. So, which essentially tells you that the gradient of your function v with respect to metric G is bounded by a constant times v. Yeah, sorry. Maybe I should write it in p r with respect of G, where constant c depends on r and x.
Sorry, this Laplacian is the 4-dimensional one?
Yes, it's with respect to metric G, it's 4-dimensional, yes.
But the right-hand side is only depending on the base, right?
Well, you can express one through the other. I just decided to write it through metric H. You can write it through metric G as well. I mean, this also, in a sense, it also depends on the base, because the exact if you write down what this Laplace operator does, it will also depend only on V and H.
Okay.
So now let's assume that your this manifold is not complete. So we can take any point on the base space, so y and n, and we can sort of start blowing up a ball until it hits the boundary. Hit a ball of some radius r, and it has hit a boundary somewhere here. So this is y star. Yeah, actually, sorry. This is of course true the entire manifold. And that's what I mean. So this point, y star is missing. So y star belongs to the metric completion of n minus n itself. This metric completion. So step 2, well, you necessarily have to, along any curve actually, if you draw any curve here, maybe let's call it gamma, then you'll necessarily have the length of this curve with respect to metric VH is infinite, and we assume that there exists a curve for which this is finite, right? That this is a point belonging to the completion. So as such, V must go to infinity subsequentially. Along gamma. But on the other hand, you have a gradient estimate on V, which you can rewrite in terms of H as gradient V with respect to H is less than V to the power 3/2. So there is a different power exactly because you have this conformal factor for the base metric here, this conformal factor V. So the fact that V's gradient V is bounded, yet it goes subsequently to infinity along this curve, they together imply that V has a controlled blow up along this curve. Specifically, V of x has to be at least some constant divided by the length squared with respect to h of gamma starting at point x. Put point x here. And as gamma is arbitrary here, what you really get that v of x is at least c divided by the distance squared with respect to h between x. Sorry, I denoted it y star, between x and y star. So with this gradient estimate, you necessarily have that your v of x must blow up at some prescribed rate as you approach this point, which belongs to your, which doesn't belong to n, but belongs to its metric completion. So in the end of the day, we want to arrive to a contradiction and show that this set is essentially empty. So there are no points which belong to the completion, but not belong to n. So this is where we use step 3. And this is, again, just kind of to give you an idea, this is a mean value theorem. So if you have a harmonic function, say in R3, so if you have Euclidean Laplace of f equals 0, say in R3, then you can compute f of 0 as the average of the values on the bounding sphere. So you have two-dimensional sphere, this sigma r. Okay. And it happens that something similar is true for v. Even though v doesn't solve Laplace equations and solve something with extra terms, you can still have for v still have a bound on integral over s to r with respect to metric h, v of x d sigma. So maybe sphere centered point y. It is less than some constant c0. But it happens that this lower bound on v forces the integral to blow up as the radius of the spheres, which you consider here, approaches the distance between y and y star with respect to metric h. So maybe let me scroll up a bit in this picture. So you can consider spheres along around y, which are larger and larger of some fixed radius r with respect to metric h. And when the sphere gets really close to this point y star, what happens is the fact that v blows up near this point forces the average integral over the sphere to also blow up. So it gives you a contradiction, and it proves that the orbit space and h is complete. So let me explain how it can be applied to study deck transformation. Okay, Yeah, let me kind of sort of just write the proposition to state. We don't have that much time. We have a moment map, I recall, from M0, so you have thrown away fixed points. Now you have thrown the generacy locus. Sorry. So this map, which you have initially here. So it's a consequence of the above result of completeness that actually the quotient space, the orbit space of this manifold actually is just can be identified with a subset or R3. So there is no open embedding anymore. So the moment map descends to a map M0 minus T to M0 minus T over S1, which will be just R3 mu minus fixed points, or rather I should say the orbits of fixed points, because it's orbits space. Modular Dirac transformation group. And this Dirac transformation group, here, gamma is either just integers, and it acts by shifting in mu1 direction. Or gamma is Z2, and it acts as shift in mu1 direction, and some other translation, preserving A plus mu plus plus A minus mu minus.
Is it really a map from M0 minus T to R3, or is it?
It will be the map to R3 modulo gamma.
Oh.
So basically, you don't have well-defined moment functions mu I. Instead, you have circle valued functions mu I. So that's the.
Yeah, that makes sense. Yeah, I just didn't see the gamma.
Yeah. So again, do I really want to go over it in detail? So the setup is above. So you take this prescribed covering with a specific gamma, and the action of Dirac transformation group, since Dirac transformation group preserves all the generalized scalar structure, in particular, it preserves the one forms d mu I. So gamma acting on M0 preserves this one forms d mu I. Therefore, it descends to translations of R3 mu. That's the idea. So now you need to explain that first, that this group acting by translation R3, that it acts freely and properly discontinuous, and as long as you can show it, you will get this reduction. Basically, you have M0 minus T moment map. The honest moment map goes to R3. You can actually glue back fixed points and don't care about throwing away fixed points here. So really, a moment map will be honestly from this m minus t universal cover to R3 mu, and it will be a surjective map. And then you have m minus t, you have action of group gamma here, and this group gamma descends to the free action here on the right. And then really your moment map descends to the moment map from m minus the degeneracy locus to this space.
Can you say again, what do you mean by R3 mu? Maybe
Yeah, by mu, I just wanted to highlight that this is not just random R3, this is R3 with the moment coordinates.
Okay.
Just to highlight that this is a specific distinguished R3, which appears here. So this is really the moment map which you have, and it factors through the orbit space. And this is isomorphic to the orbit space. So this really the key part, that we know sort of exactly what the action of gamma is, and we know that completion of this thing should be precisely the orbit space of our soliton. Completion with respect to H of R3 mu modulo gamma must be isometric to m modulo S1. Well, with respect to the metric which you can cook up from it. So you take G, you take its horizontal component, and you multiply it by V inverse. So, okay, well, I don't have that much time. Maybe let me write down the statement of the classification. Basically, what I'm going to do right now, I explain which viable completions occur here and which functions V you're allowed to take to get the complete solution upstairs. So it happens to be that there are two really different cases. So there are two cases for what this completion is. And they're controlled not really by group gamma, but they're controlled by whether A plus and A minus are both non-zero or one of them happens to be zero. Case one, where A plus and A minus are non-zero. So, and I assume that this gamma is isomorphic to Z. So this is really the most interesting case to my taste. So then in this case, I will call this gadget N A plus A minus. So well, let's see. So this was R3. We have quotiented by gamma. When you quotient it by gamma, it becomes a product of R squared and S1. And then you need to understand what is completion. And since magic H is fairly explicit, it is possible to do so. And I can draw a picture here. So this A plus A minus looks as follows. It's a spindle, by which I mean S2 with two conical singularities. So here you have angle P A plus. Here you have angle, pi A minus. So this is something two-dimensional. You multiply it with R. So this is how the completion in this case look like. And case two is when A plus is say non-zero and A minus is 0 and gamma is still integers. So in this case, what you get is something similar. You'll have A plus times R. And maybe let me call it N A plus 0. Okay. You have these two pictures. Now the question is, what if I allow gamma to be larger? What if gamma is z2, this is z squared? This was the second option which I discussed. Well, then the things work as you would expect. So this z acts by translations in R composed with rotations here. And similarly also it will be translations in R together with possibly trivial rotation in this component. So what this description tells us, it gives you a quantization of A plus and A minus. Since if you think about A plus A minus must be isomorphic to as a manifold with conical metric. It must be isomorphic to the quotient of M modulus 1. And what we know about action of S1 here, that it has either fixed points, isolated fixed points with weights plus or minus 1, or it has finite isotropy groups. And finite isotropy groups, they occur on the locus I equals plus or minus J. So whenever you have a finite isotropy group of S1 action on a codimension 1 divisor and you take S1 quotient, you exactly encounter a conical singularity like this, cone angle times an interval. But this angle will be special. It will not be just pi times some real numbers. Cone angles in the second case are pi over 2 pi over k, where k is the size of the stabilizer over point x. If your x belongs to M. So since cone angles on the right-hand side are really possibly could be only 2 pi over k, it forces these constants A plus and A minus also to be 2 over k. This is something, some phenomenon which we didn't really anticipate in the beginning, but it happened that we necessarily have that A plus is 2 divided by integer and A minus is 2 divided by integer, or 0. They could be 0. So now let me discuss construction for a second, and then I will say what classification tells us. Construction of solitons. Let me start with a case where A plus and A minus are non-zero. and the depth transformation group gamma is Z. So then our input will be this. I draw it a bit differently. So this will actually. Anyway, so yeah, I'll draw it like this. So this will be my N. And A plus, A minus. And recall that due to the quantization, I want it to be 2 over K plus, and I want this to be 2 over K minus. So then what I allow myself to do, I allow to take a finite collection of points in the smooth locus of this guy. Finite collection in the smooth locus. Then there exists a function v of x sorry. So this color points, let me denote them yi. So for any yi, there exists a specific special function which I denote g y of x, such that first L of GYI equals negative delta I, delta YI, where L is that operator which we apply to function V. And V of X, which equals constant sum yi of X solves L V equals 0, or maybe rather on the complement of this point. And gives rise to a complete generalized scalar rank 1 soliton. M G I G. So let me talk a bit about these constants. And actually, I'm about to write one more part here. So these CIs, they are actually frozen. It's they are prescribed. It is like it happened with Gibbons-Hocking ansatz with the classical with Haber-Keller. So these constants which you could put in front of monopoles, they are prescribed, and these are like your monopoles. So these are fixed. You can try to change them, and you can change them in a discrete set. And if you do that, then you can still construct a complete generalized scalar rank soliton, but it will be an orbifold. So it's fixed points, it will be orbifold fixed points. So this is an C is any positive real constant. And there is one extra thing, that there is actually one sort of anomalous freedom, which I will denote as G infinity. There is one extra function which could be put here. So there is C2 prime. So it sort of corresponds to a pole at infinity. If you think about this as S2 cross R, S2 cross R can be identified with R3 minus the origin. So this corresponds essentially to the Green's function at the origin. So again, how does it work? So we first choose parameters A plus and A minus. So they prescribe n, A plus, A minus, the orbifold together with the metric H. This is what you have. Then you make arbitrary choice of points in the smooth locus. And for points in the smooth locus, the claim is that you can solve this equation. We should write that it is positive and goes to 0 at infinity. So yeah, I have written here exists. Actually, they are fairly explicit. They're not super explicit, but you can you can manage them. These functions, these monopoles. And then you have this family. So this is a free parameter C. C star is also a free parameter, but it also quantized. So there is this funny quantization business. So it really belongs to C0 times integers. So this is the first case. So then there is case where A plus is non-zero and A minus is 0. Well, it will be almost the same business, but now you'll have this to be 2 over K plus. It prescribes orbifold with a metric as above. You're allowed to take finitely many points in the smooth locus. And in this case, similarly to the above, your V of x will be positive, non-negative constant plus sum of Ci Gy I of x. So it's a bit different. So C is allowed to be non-negative here in this example, and you don't have this anomalous solution. Other than that, the picture is similar. Equals C. So now if gamma equals Z squared, then no fixed points. You're not allowed to take any fixed points. So basically, you don't have this term, and you don't have this term, and you need to take the quotient of this orbifold or this orbifold by Z, by translations in Z. And if you do it here, you will still get something complete, non-compact. It will be specific soliton with no fixed points. If you do it here, you will get something interesting. If you take Z quotient of this gadget, you will have something compact. And the compact thing which you will obtain here will be precisely the Hopf soliton solution, which we see, at least on the level on the metric. There is a little caveat. Sorry, I'm running out of time. Maybe I'll just briefly mention it. So if you think about Hopf surface solitons appearing from this picture, you will really have this one form which I discussed in the beginning today. So this one form, it will be closed but non-exact. So in this sense, Hopf Hop surfaces are not really rank 1 solitons. They will become rank 1 solitons as long after you take universal cover over them, but they are not universal cover on the nose. So here you're really not allowed to take gamma to be z squared if you want to get a true soliton where you have a non-soliton function. But if you're fine with having soliton closed 1 form, you can take z2 here as well. And here you can take z squared, and it will give you a genuine soliton. So this is the construction part, and maybe I'll just finally write down that this construction is exhaustive, meaning that all complete rank 1 gradient steady solitons with S1 action and technical assumption that you need lower Ricci bound are obtained from one of the described pictures. So sorry for running over time. I'll stop here. Thank you for your attention.
Yeah, thanks, Yuri. Are there any more questions?
How important is it for the F to exist?
For F to
rather
exist?
than-
Well, I know that people in physics, I mean, the people studied these equations, they don't really care as long as you have a closed form in this equation, they're pretty content. But from the point of view of the functional, it is important. So functional, F functional, to give any meaning to it, you want F to be a genuine function.
When you apply the Ricci flow, does it still kind of evolve in a nice way?
Just usual Ricci flow?
Well, the generalized one that applies.
Well, if you apply for these examples, it will just flow by diffeomorphisms, depending on the gauge which you choose. It will flow by diffeomorphism either along VI or with J. If you take I fixed gauge or J fixed gauge, or if you take the neutral gauge, the effect of the flow will be adding a constant to function phi. So you remember this function phi, it was a linear combination of mu plus and mu minus plus a constant. So the effect of the flow will be just increasing this constant in the linear speed.
I guess like in terms of the classification result, there's no like assumption about this F. I mean, like when we assume
this function F.
I mean, we assume the soliton PDE in particular, which does indeed give you like, which comes equipped with an F, right?
Yeah, but you can write the same soliton equation, just saying that it's not F, but it's comes from some closed 1 form.
Well, yeah.
So that's how people in physics write it. So they don't really write hash and F. Instead of hash and F, they write grad of closed 1 form.
Right. But I guess maybe my point is like in the end, we're just assuming the PDE and the actual rank 1 hypothesis is really just IVI is a multiple of JVJ, right?
Yes.
I mean, that's really all that's being assumed.
Exactly. Yeah. Yes, that's true. It's just to write down the classification. It's either will look a bit ugly because you have to consider cases, or you want to allow in your understanding of what soliton is, you want to allow for a non-exact 1 forms. But yeah, classification, sort of classification even goes slightly beyond what we have stated. That's what I want to say. So we really classify also examples where there is no F, but only closed 1 form. Are there more questions?
Well, yeah, thanks again, Yuri.
Thank you.
Stop.